Then how would never mind, I'm not going down that road. It's like, how would I know that you got it?
It's like my foot or something.
Oh, okay. All right.
I'd probably do it first credit in this class.
What was I doing? Anyway, I was doing. How's everybody doing? Doing? I need to get that file.
The one from the other day.
Yeah.
Watch Grey's Anatomy?
I do. I haven't seen it for a few weeks, though.
I haven't seen it for the last 2 seasons.
Oh. I was like, well, don't spoil anything.
No, I'm on the shooter episode.
Which shooter episode?
Where that guy whose wife died comes in.
That's more than a couple of seasons ago.
I know. I'm rewatching it.
Oh, okay. I was like,
I've already seen it like 4 times.
That's like.
I just rewatched it. That's all.
Well, it's like 7 seasons ago, isn't it? It's a long time.
6.
Okay, so it's 9. It's like 9 seasons ago. This is 15, I think. What?
I don't like that show.
You don't like that show?
The first couple of seasons were like, oh, this is good, and then like stuff keeps happening. You're like, is this really like not realistic?
I watched the first episode and there's too much blood, so I turned it off and
There's definitely a lot of blood.
That is true.
it's that man that has Alzheimer's, and that she's like reliving all these events, and that's why they're so exaggerated. It's so unrealistic. It's like her retelling.
That would be strange.
They're on the season right now, aren't they?
Yeah.
It's literally like season 14 or 15. Isn't that crazy?
All right, let's look at. Let's look at. This is the data that's on the sheet 2. That's in the sheet that I sent you last time.
Is this a homework problem? I mean, not in the book.
Is it in? It's number 10 in the book, 8.1-10. Okay, so the idea behind this one is we've got this data. This data represents the distance between bad records on a used computer tape. That means a lot to you guys now, for sure. But anyway, so it's how many. What did it say? It was a distance in. I don't know. It doesn't even give you a distance in however long it was. Doesn't matter. This is between bad records, so basically you're going along and it's the first occurrence of a bad record. And then going along again and it's the next occurrence of the bad record and so on down the line. So the distribution for first occurrence of something, what kind of distribution do you typically think of if it's time until first occurrence? What kind of distribution? It's exponential, right? An exponential distribution is typically first occurrence of something, right? So what they want to do is see if we can, if this data makes sense to come from an exponential distribution. Now your exponential distribution, what does your PDF look like? Okay, cool. So if this is your exponential distribution, this is your PDF. What's your CDF look like? Just because we're going to use actually the CDF here in a second. Those are pained expressions.
Yeah, I don't know. CDF.
There you go. There's our CDF. Cool. I'm going to want to use this in a minute. But in particular, notice that we have the parameter in either of those things. We have one parameter, right? Now, in general, you're not going to be given what that parameter is to try to figure out, does the data that I have match this particular distribution with that parameter? Right? Think about it. I mean, the whole point of this is trying to do this stuff in real life, if you will. Okay? So if we're going to see if this data comes from an exponential distribution, which would make sense that it would come from an exponential distribution because we're looking at time until, or in this case distance until, but time until first occurrence of something. And we also know that once we hit a particular time, if we go on to the next one until the next occurrence, we know that that also is exponential. That's that memoryless property that it has. But we still have exponential on that same length of time. Okay. So in particular, we think that the exponential would be a good model, but in an exponential, I have a parameter that we have to try to figure out what it is. So we're going to have to estimate that parameter. Now for exponential, how do I estimate what this theta is? What would I use to estimate the theta? The mean. Good, because the mean is theta, right? And it also happens to be the maximum likelihood estimator from the sample as well, correct? So we would use, I can spell the word use, holy cow, use x bar to estimate theta. And again, the reason why we would use our x bar to estimate the theta is because theta is the mean of the exponential distribution, but also when we did our maximum likelihood estimator stuff earlier this semester, given a sample, the thing that has the maximum likelihood of being the parameter we're looking for the exponential is the mean. So it makes sense to use the mean in that case, right? So we can figure that out pretty quickly on Excel because I can just highlight that. It even says 42.2 down there after I've highlighted it. But if I just say equals the average of that, I should get 42.2. All right. So our goal here is to see, okay, if I put 42.2 in for theta, does it seem likely that this data came from that particular distribution where I used 42.2 for theta? Okay. So what they asked us to do in this particular problem is to look at intervals that would give us equal probabilities for which data should fall into. So what I mean by that is, if I think about the picture for exponential, your exponential distribution looks like that, right? Okay. So what we want to do is, it tells us to use 10 intervals, so 10 different classes to break it up into. Okay. So I would need to find different data points where this is 0.1, this is 0.1, this is 0.1, and so on down the line. So I would have, for lack of better letters here, I'll call it gamma 1, gamma 2, gamma 3. I want to find those endpoints, and then we're going to count how many of the occurrences in our data are in each of these intervals. Now, remember, we talked about this last time where we did observed minus expected. If I take 10 classes, there's how many data points in this case? 90, I think it is. If I take 10 classes that have equal probability of happening, how many should we expect to see in each class? If there's 90 total, 9, right? Because we're doing equal probability, right? So we would expect to see 9 in each of these classes, okay? And it will count up how many there are in each class, but we should expect to see 9, right? Okay. All right, so how do we find these endpoints? Well, this is where our CDF part can come in here for us, right? So the CDF counts, of course, from 0 up until this point. So to find gamma 1, I would put in 0.1 for f of x and figure out what the x is. For gamma 2, I would put in 0.2 and so on up the line. So in general, we would have, if I say this is my p, then I would have e to the minus x over theta is 1 minus p. Take the log. and then multiply by negative theta. Right? That's how we would find those x's. The reason why I actually had to solve this equation is because there's not an inverse exponential distribution in Excel. Otherwise, I just would have used the inverse exponential distribution in Excel. If there is, I didn't find it the other day. All right, so first, the thing I want to do is type in 0.1 and 0.2 and go up to 0.9. And then we're going to do A11, because that's the average, make it absolute cell reference, and then multiply it by the natural log of 1 minus the probability that's over in A. Oops, I need a negative, don't I? Sorry, I need a negative out in front. Sorry about that. The A11 again here is our theta, right? That's the estimate for theta that we're using. It was the mean, right? So I'm just using this formula here. So I've got negative times the theta, and then natural log of 1 minus the p, and I just have my probabilities going from 0.1 to 0.9. Because when I go from yes.
Why did we choose 0.1?
Because we want it into 10 classes. The problem says to put it in 10 classes. So how many ever classes it tells you to do, that's why we're going to use that probability divided by that. We'll do 100% divided by that much. It just depends on the setup in particular. All right. So that's why we use those. I'm just trying to divide it into 10 classes that have equal probability. All right. So we'll do that in this particular case and hit enter and then copy that down. All right. So those values that I have there are your gammas. Those are the gamma 1, gamma 2. I just label them gammas. The letter doesn't matter. I just picked a letter. And didn't draw an emoji because apparently people get mad when I draw emojis. All right. So what we need to do, and not do it by hand because that's not fun, is I need to count in our data, and I can't see my last number there, in this data, how many are between 0 and 4.44, how many are between 4.44 and 9.41, and so on down the line. That doesn't sound like something that's fun to do by hand, okay? Well, luckily, Excel has a COUNTIF function. I think we've talked about the COUNTIF function just before, perhaps. If not, there's a COUNTIF function. All right, so in the COUNTIF function, the first thing we're going to do is highlight the array and make it an absolute cell reference on the array because I want to copy it down. Okay. The first range is I want to count if it's less than or equal to that 4.44, right? Okay, so quirky thing in Excel, the less than or equal to is a logical operator that we could use, but I have to tell it that I'm typing it in Excel as string elements, as like letters, and then have it go back to cell references. So to tell it that it's a string element coming, I got to put quotes around it. So I got to do quotes less than or equal to. So I just literally typed in a quote, a double quote, I guess, quotation mark, less than sign, equal to sign, end your quote. And then I have to compare it to something. And I can't just put the cell reference in next because it'll give you an error. You have to tell it that a cell reference now is coming. To do that, you have to put an ampersand. And then refer to the cell reference, which is B12. Okay? So there's 8 of them. All right. Now, I don't want to, I'm going to copy it down to the next one. and where it says 18, that number is not really 18. Because when I copied it down to the next one, notice it says just if it's less than or equal to B13, right? Right? But I don't want if it's less than or equal to just B13 because it also counts the ones that are less than 4. Correct? So I'm going to go up and edit this cell. I'm going to copy that COUNTIF statement. I'm going to put a minus sign. I'm going to paste the COUNTIF statement and change the previous one to B12. So just to say what I did, let me hit enter and then actually you just click in this cell so you can see it. It's a little bit bigger. This counts everything that's less than or equal to the 9.4, and we're subtracting off everything that's less than or equal to the 4.4, right? So I'm counting the ones that are in between. And then I'll take this and copy it down, because now it'll do it like I want. It'll subtract out the ones that we don't want. So hit enter. All right, so this is less than 4.4, between 4.4 and 9.4, all the way down to between 67.9 and 97.1. We also need the ones that are bigger than 97.1. If we've done everything correctly, that should be the rest of them, right? We know there's a total of 90, and the rest should be bigger than that. Okay, so we can check that. Notice we got a sum of 75. Right? So sum of 75 for what I've highlighted, plus 8 would be 83. So there should be 7 left. To just check that, I can do a similar statement. Let me copy this down one more. I'm not going to copy down one more spot. I'm going to type in if equals COUNTIF, and then highlight my array again. And then I want it greater than or equal to, or strictly greater than, that B20. I'm just checking to make sure we really count them all. That's all I'm doing. I know that this should be 7, right? So when I hit the enter key, how is that confidence? When I hit the enter key, we're going to see 7. And no, I hadn't done it before I came in. I mean, I've played around with different ones. I haven't done this particular problem yet. I was very confident that Excel was going to do it right. More confident than this stuff working in numerical. All right. Anyway, these are our actual counts. These are the observed values, right? You just told me that all the expected values are what? If we've cut this into, we've got 90 data points, we've cut these into equal probabilities, what should be your expected values for all of them? 9, right? You told me that a minute ago. So I'm literally just going to put 9 in and copy it down. And then remember, for your chi-squared statistic, we want to do observed, which is 8 in this case, or the C12, minus expected, which is the 9, which is the D12. We square it and then divide it by expected. Remember last time we talked about how this gives you an approximate chi-squared distribution, right? Talked about this last time? Okay. Let's pull this down. This gives us our chi-squared statistic. So if I do the sum of those, when we sum that up, we get 2.8 repeating. 2.89 there. That's our chi-squared statistic. So we want to check that against a chi-squared distribution, and see what the p-value is. Okay. The important thing now is if I want to, because we're doing hypothesis testing, we're doing this against the chi-square variable. The important thing is, of course, now we need to know how many degrees of freedom we have. Now, remember last time we talked, we set it up with just an either-or situation, and said if you're in one, then you know what the rest of them had to be in the or part. This isn't quite either-or, because we've got it set up as 10 classes. But once we know the first 9 classes, the 10th one is determined, right? Even though I put a count if statement in there, I knew what the last count had to be before we even started. So, even though we have 10 classes, the fact that we know what happens in the 10th one cuts 1 degree of freedom off, right? So that already cuts it down to 9. Now, were we given the value of theta, or did we estimate the value of theta? Estimate it using the sample, right? As soon as you estimate a parameter, you lose another degree of freedom. Okay? So we lose 1 degree of freedom because we know the last class is completely determined, right? It's dependent on the other 9. We also lose a degree of freedom for every parameter we estimate. So here we estimated 1 parameter, we lose 1 degree of freedom. If you were doing a normal distribution, how many parameters does a normal distribution have? 2, the mean and the variance, right? So if you use the sample to estimate both of those parameters, you lose 2 degrees of freedom for that.
So this is because we estimated theta.
It's because we estimated theta, right? So you lose another degree of freedom. Exactly. So we had 10 classes, subtract 1 because the last one's completely determined by the other 9, subtract another 1 because we estimated theta. So you lose 2 degrees of freedom. So what we want to check here is, we want to check the right tail on the chi-square distribution and look for the p-value. So I'm going to do chi-square right tail. I'm going to use the chi-square statistic that we just calculated, which is in E22. And I want to do it on 8 degrees of freedom. This is going to give me the p-value for the hypothesis test. Our null hypothesis here is this is an exponential distribution. Okay? That's our null hypothesis in this case. In fact, it's an exponential distribution with theta equal to 42.2. That's our null hypothesis here. Okay? So we want a high p-value. A high p-value says we're going to accept the null, and we really do have a decent model for the distribution. A low p would say that we didn't have a good model, go find another one. Okay? That's a high p-value. It's exceptionally high p-value, probably because they actually took the exponential distribution and took those points out of it, randomly selected. Okay. All right. So in this case, you would accept the null. The high p-value says it's a good model, so you would use that. Now, again, as you had more data, you would adjust your theta and retest. But this is, I mean, this stuff is honest to goodness done in actuarial work. You go out, when you look at claims, you look at how those claims are distributed so you can set premiums. Well, you don't have, somebody's not going to say, hey, look, here's your distribution. Okay? You're going to collect data. You're going to look at that data, see what kind of distribution it might fall under, test it, and use your parameters to, or use your data to estimate the parameters, and see if that really does work. Well, at least model, I should say, work. But then again, as you collect more data, you adjust the model. So you do this all the time as an actuarial. That's why actuarial tables get adjusted all the time.
So by accepting the null hypothesis, we're saying that the exponential is a good
Is a good fit. Yep. Yep. That's exactly right. So is that right? So again, here we use the fact that we broke it into cases. If you wanted to try to get this even more pinned down. Perhaps you wanted to do more classes, you could. This one is the problem told us to use 10. We could have used 20. We could have used 5. It all depends on your choice. This one okay? Any questions on that one? Let's do one with a Poisson here. Bless you. Let's look at number, this is number 9. This is 8.1-9. I don't have the data typed in for this one. There's just not that much data. So this one says there's 40 observations. We yielded 5 zeros, 7 ones, 12 twos, 9 threes, 5 fours, 1 5, and 1 6. So I'm going to put 0, 1, and then copy this down to 6. Oops.
Why did you see sheet 8?
Because I opened a new one.
Oh.
And I have no idea why I put it in between 2 and 3.
Yeah, I got really good.
Only because I think it was because I was in sheet 2 when I hit add a sheet.
Mine said sheet 1.
There we go. I moved it to the end because it was bugging me. Having sheet 8 between 2 and 3 was bothering me because I'm weird. All right. The problem said there were, what did I just say? 5 zeros, 7 ones, 12 twos, 9 threes, 5 fours, 1 5, and 1 6.
What problem was this again?
8.1-9. So this is number of flaws per 100 feet of tape, because of course it is. Now they tell you, in the problem they actually tell you what to use for lambda, but say they didn't tell you what to use for lambda. How would we get an estimate for lambda? The mean again, right? So they'd be mean per 100 feet. So I would need to multiply the 0 and the 5, the 1 times the 7, the 2 times the 12, right? Because it was 12 error. I'm sorry, there were 2 errors 12 different times. There were 9 errors 3 different times, and so on. I could do that, but there's also a sum product command in Excel where I can just multiply them all together. It doesn't basically does a dot product. So for sum product, I want to take the ones that are in column A and multiply them by the ones that are in column B. And then divide by how many total records there were, or how many observations there were, and there were 40 total. I mean, I could get the total number of observations just by doing the sum of the column B. That's interesting. 2.225? Okay. Sure. The problem says to use 2.4, but that would be the mean, right? That's the way we would use. If we wanted to estimate the lambda, that's what we would do, right? Find the mean. So again, all I did was the sum product command just does the product. It's doing the weighted average idea, right? It's doing a dot product. It's taking the value times the number of occurrences. So it was 0 times 5, 1 times 7, 2 times 12, and adding it together. And then dividing it by the total number of occurrences, which should have been 40. If I do the sum of that, that should be 40. Yeah, so. Does that make sense? We okay with that? All right. So we can use that value, that 2.225, to give us the expected number of times we see 0 or 1 or 2 and so on down the line, right? In Excel, the Poisson distribution is built in, the Poisson.dist. I have no idea what that last one is. Ret case and poista. I don't know what that even means. Okay. All right, the Poisson, notice it says look for the x value and then the mean and then whether or not it's cumulative. Well, the x value is over there in A1. The mean, you can't see it, but it's in D1, right? That's where we computed the mean. I want to absolute cell reference that because I don't want that to change when I copy it down. And then I want probability mass function here. I don't want the cumulative one, so I want false for that. I'm just going to type in false. I don't want it cumulative. I want it as a probability mass because I want to know probability that 0 occurs, probability that 1 occurs, and so on down the line. Now, those are probabilities, right? Not expected values. There's a couple of things I have to be a little bit careful of. First, those are probabilities, so I have to change it to expected values. There's one other thing that I have to be careful of. Notice I copied this all the way down to 6. For a Poisson distribution, that's not all the possibilities, right? It could be 7, it could be 8, it could be 9, and so on down the line. Notice down here where the sum's computed, it says 0.99, right? I didn't take care of all the probabilities. This last one here, I don't want to necessarily compute the probability that it's actually equal to 6, right? I want 6 or more. Even though that's the last data that we're given, I know that the end of it is kind of the Poisson tail, right? So what's probably better to do, instead of computing it this way, is changing this to 1 minus the sum of the previous ones, doing the complement here. Now everything should add up to 1. Again, the reason for that is that the Poisson distribution doesn't stop at 6, right? It's 6 or more.
So, A is observed and then B is expected.
It's probability. No. A is number of occurrences. This is observed.
Okay.
I haven't done expected yet.
Okay.
I'm calculating the probability so I can do expected. To do expected now, how do I use the probabilities to find the expected number? What do I do? How many total observations were there in this problem? 40. So what do I need to do with those probabilities to figure out expected number? I've got probabilities. I know how many total observations there are. What do I need to do to get expected number? Yeah, just multiply them. Good. I just need to take each of these probabilities, the C1, and multiply by 40. I could have done that all at once, right? I was calculating the probabilities. I could have just put that in the same column. All right. Okay.
That's expected.
That's expected, yes. All right. Before we go on, the rest of this is exactly what we've been doing now. We calculate the chi-squared statistic and get the p-value. Before we go on, however, I want to point out one thing. These values on the tail are small, right? The Poisson, certainly the bigger the x gets, the smaller the probabilities get for a Poisson. So it's possible that these last ones here, now it's not doing it in this particular problem, but it's possible that these last ones here can get easily skewed by really small probabilities. What I mean by that is, say that this expected value here was like 0.3. Right? Say the expected value was 0.3. Well, if I had an expected value of 0.3, but I actually saw one observation, you would have 0.7, right? You would square it to get 0.49, but then you would divide that by the 0.3. So you would get a piece in your chi-squared statistic that's, what, like 1.7 all by itself? If I get something that's close to 0.9, if I divide by 3 is 1.67, right? It's 2/3, 1 and 2/3. What I'm saying is that if you have a low expectation here, but you've got an observation that might have actually occurred, just because it's a low observation doesn't mean it's impossible, right? But if you've got a low expectation, remember what goes in your denominator. You do observed minus expected squared and then divide by expected, right? If you divide by a small expected, you can get a big number for your chi-squared statistic where you don't necessarily want it. Okay? So one of the ways to combat that is it might make sense in this particular one to group these together. This one's not as bad because I got the 1.04. I'm going to subtract the 1, so it's going to make it small on top anyway, right? But in general, it's possible that you could have small expectations that you're going to divide by, and it's going to skew your chi-squared statistic. So you might want to group these two together. So group 5 or more together and make a probability there if it's small. Remember last time we talked about the reason why we're using an approximate chi-squared is because we've got an approximate normal distribution that we squared with those proportions. For that to be approximately normal, we have to have the n times p to be bigger than 5. That's not bigger than 5, is it? Right? Now, I'm not saying that all the time you'll make it bigger than 5 because it may not be possible or it may not be prudent. But it might be the case that you want to combine these two. You might want to combine the last 3 here to make it bigger. It depends on what the values are. You don't want one particular class to skew it just because the expectation is small, is what I'm saying. Okay? So you might need to group classes. I don't think it's going to matter here because when you do this subtraction, it's going to be small anyway. That makes sense? You just have to be mindful of that. If you've got these expectations that are small, you're going to be dividing by those expectations that could blow up that one particular term and skew your results when you don't want it to. See, if it looks like that's happening, combine things.
So we just drop the 6 and then make the last one 5 or more?
Yep, make it 5 or more. You would combine those two probabilities together and combine your expectation. So you would do 1, and what we did 1 minus on this one, we would do 1 minus that sum to get that probability, and then make this a 2. And just group them together. All right. So now we can do observed minus expected squared divided by expected, and copy it down and add them up. So same stuff we were doing, right? We did observed minus expected squared divided by expected, and then I just added them together. To check the p-value now, I'm going to do the chi-squared distribution right tail again. The x value we're going to use is up there in G8, where I have it typed right now. The last question now, of course, is how many degrees of freedom? Well, how many total classes do we have here? How many? 7, right? We did 7 calculations, right? But remember, for degrees of freedom purposes, we lose 1 for what? The last one, right? And we lose 1 for what else? Yeah, estimating the mean, right? So we should have 5 degrees of freedom in that case.
But didn't they give us the mean technically?
They did, but we used the estimate instead. Okay. They gave us the mean, but which was actually a different value than what we calculated.
So if we just use the one they gave us, we wouldn't do that.
Right. If you use the one they gave you, then you're not estimating that mean. You're using the one that was gave you, so you wouldn't take one off for that. But anyway, what do we say about that p-value? Is that high or low? That's a high, and high is what we're looking for, right? High says good fit. that make sense? Questions about that at all? Let's jump over to, let's do one more with a normal distribution. Let's do sheet 3. You have to be careful when I say sheet. 8.1-11. The problem in the book says to group the data into 9 classes of equal length with the class boundaries that start at 2.125 and end at 2.145. So let's see if this will actually follow the pattern. Yep. Should have 9 classes. So 1, 2, 3, 4, 5, 7, 8, 9. If I did that right. 1, 2. Yeah, that's 10 numbers, so that should be 9 classes. I only used those numbers because the book said to use 9 classes of equal width. Okay? And it says to start at 2.125 and go up by 200s each time. All right. We want to count the number of observations that are in each class. Okay? So we'll use the COUNTIF command again. Take the array, make it absolute, and I want it less than or equal to that first value.
So you want it on the second one?
Yeah, because there's only 9 classes, even though we've got 10 points.
Oh.
Yeah. I don't even really need that first point at all. I only needed the first point to tell me how long the things were. Because for our purposes, between 2.125 and 2.145 is just going to be less than 2.145. And just so that I don't have to, well, nope, I had to do it anyway. Just so that I don't have to retype it for the next one. There shouldn't, in the data up there shouldn't be anything less than 2.125. If there was, that's a badly written problem. So I'm going to go ahead and just put the minus part in there now so I can just copy it down. I want what's in between the two, just like we did last time. Count everything that's less than the higher limit and subtract off everything that's less than the lower limit. And then let's just copy this down. Oops, maybe. And there are 100 data points, and we've got all 100 of them now. Now, just looking at the distribution, the way this came out, this is just a relative frequency distribution. Does it look like it's mountain-shaped? Does it look like it's high in the middle and lower on the ends? I mean, it's turned sideways, but does it look like it's mountain-shaped? I mean, if we're thinking these came from a normal distribution, it better be mountain-shaped, right? If you don't have something that's mountain-shaped, normal is probably not good to start with. Do you agree? Okay. All right. We're going to need to estimate a couple of parameters from this distribution. I need to estimate the mean. I need to estimate the standard deviation, right? Well, mean's easy because I can just do average and then highlight the range here and get the mean. For standard deviation, we want the stdev.s, That's standard deviation of a sample. And then highlight. So I now have estimates for mean, estimates for standard deviation. So now I need expected values that are in each class. Or in particular, I have to be a little bit careful. This 2.145 is everything less than 2.145. This between 2.85 and 2.3, remember these are the upper limits. They're next to the upper limits. This 1 right here, even though I counted between 2.285 and 2.305, that's actually everything that's bigger than 2.285. Okay? So for our purposes for normal distribution, when I do the probabilities here, I want probabilities for the normal distribution. So norm.dist. The x value that I want is over there in A13. The mean is up in C11. I'm going to absolute cell reference that. The standard deviation is up in D11. I'm going to absolute cell reference that. And then I do want cumulative, so I'm going to make that true. Before I hit enter, well, nope, not before I hit enter. Go back into it. I want to copy this because I'm going to use it in the next one. All right. That gives me the probability that things are less than the 2.145. Okay. In the next one, I want the same thing with A14. That will give me everything that's less than the A14 value, but I want to subtract off everything that's less than the A13 value. That was why I copied it. All right, so again, this first probability, almost out of time. The first probability is for everything less than a 2.145. These next ones now, up until I get to this point, I want things that are between the two values. So that's why I've got the subtraction. All right, so we'll copy that down until the very, very last one. And then for the last one here, I want to do 1 minus the sum again. Because that'll be everything that's bigger than the 2.285. Those are probabilities. There's 100 data points, so I want to take each of those times 100.
Everything that's bigger than the 2.285 or 0.305?
The 2.285. Yeah. Because those ones I use the right endpoint to get those values. So it's everything. So that's everything that's 2.285, 2.305. I want to multiply each of those by 100, and then do our chi-squared bit. And I know I'm going quickly now, but that's because I'm out of time. Okay. Here's what I just mentioned a little bit ago about issues with small expectations. Look at that last chi-squared number. You got a 7.55 in that last expected value. That's really skewing things, right? And again, the reason why is because this expectation is very low, but we saw one. So to fix that a little bit, we would probably want to combine the last two. I'm not going to, just in interest of time. But now we can do our p-value again. No, I didn't add that up, sorry. Let me add it up first. Sum. And then the p-value. How many degrees of freedom do we have on this one? How many classes do we have? And there's 9, right? So we lose a degree of freedom for the last class. So that's 8. We estimated how many parameters? 2. So we're down to 6. That p-value is not very high, right? But again, part of the problem here is what? That last class has that small expected value, right? So it probably would make sense to go back, combine these last two classes, and see what happens.
I got 0.4, 541.
How many degrees of freedom? Did you get the same sum? You have 11.51? Did you add those? Did you add, what do you have for your sum? Do you have the other values that match?
You put 2 in the observer.
Oh, you combined them?
Yeah, that's what I meant.
Oh, okay.
That's what I meant when I got. But would it be different degrees of freedom?
It should be 5 degrees. If you combine the 2 last classes, you should have 5 degrees of freedom instead of 6.
I got 401.
Cool, good. I didn't do that. I didn't combine them.
That's what
Yeah.
I meant. I was
Yeah,
trying
yeah,
to say,
yeah.
actually.
Yeah. So 5.54 is pretty good, right? Okay. So that's actually pretty good for a p-value for fitting. Okay. I mean, it's not as good as the other ones, but those were all rigged. Okay. Where this one's not as rigged because it's actual data values that were collected. Okay. Where the other ones are rigged. All right. Have a good one. We'll see you on Friday.